And so let's call this a revision of statistics. And the first thing that we started with the statistic, that was the descriptive statistic. Which basically helps you to summarize some data. And we said a typical measure of central tendency is the mean, median, and mode. The mean simply is the arithmetical middle. The median is when you find out what is the center of your data, and the mode indicates which of the data frequency occurs the most. And of course, you're familiar with all of these things. We also discussed a measure of not central tendency, but measure of dispersion, how different your data in a data set are. So we said, for example, you've got x1, x2, x3, and so on and so forth. These are your individual observations. And it's very unlikely that they are all the same. If they are all the same, that means that you obviously measured very, very accurately. But in practice, this actually doesn't really happen. And with the measurement of the dispersion, you measure how widely spread your data will be. And we said we can calculate a variance. So we can calculate the variance of your data, and we discriminated between two scenarios. We said it could either be a population that we are looking at, or it could be a part of a population. So the population would be all the data that are theoretically available, or we just take a subsection of this population, and that is what we call sample. And we said in terms of population, the way we calculate the variance would be, first of all, we take our individual data set, x1 minus the population mean, which is usually abbreviated by mu, squared plus x2 minus mu squared plus x3 minus mu squared plus, and so on and so forth, divided, and since we are talking about a population, we divide it by the number of observations that we have. So that would be divided by n if we have n observations. So that's the population variance. The sample variance would be x1 minus x bar. X bar indicates that this is the mean of the sample. So the mu indicates this is the mean of the population. But if we just take a sample, we don't know the mean of the population, so we use the mean of the sample. So x1 minus x bar squared plus x2 minus x bar squared plus x3 minus x bar squared plus, and so on and so forth. Because it's a sample, we divide the thing by n minus 1. So when you hear sample, it's n minus 1, please. Yeah? Make sure that you don't forget n minus 1 sample. If you want a sort of a mnemonic, you've got an m in here, and m in the alphabet, m equals n minus 1. So it's one letter before the n. If you really need to recall it that way. Something that we haven't talked about, and which I want to quickly put in here, you know that I have this slight obsession with units. And what would be the unit for the variance? The unit for the variance, if you just simply look at what we've got here, we have the unit for x, for our data, squared. So the unit for variance would be unit for our data squared. So if you have, for example, if you measure the height of people, the unit for the variance would be centimeters squared. Yeah, so don't forget units. So that was the variance. We also said we can use the sample, well, we can use the standard deviation. And because we have two different things that we can look at, we can use the population standard deviation, which is usually abbreviated with a sigma. Sigma equals the square root of the population variance So that means in this case you would have an n in the denominator, or you can have the sample standard deviation, which is abbreviated with a small s, and that is the square root of the sample variance. So in this case we would apply n minus 1 here again. Yeah? Good morning, good afternoon, good evening. So what's the unit for the standard deviation? Loud? It is the unit for the data. So unit for standard deviation is unit for data. The reason for that is because we've got unit for the data squared. For the variance, we take the square root, so we end up with the unit for the data. And that is actually why people introduced this strange thing called standard deviation, because they wanted to have it the same units as the units for the data. Yeah? And that was the reason why people wanted it to be taken the square root of that. Does that make sense? We have another measurement, which is called the standard error of the mean, short SEM, standard error of the mean. And that is defined as S divided by the square root of n. S is the sample standard deviation, n is the number of observations. And that is our standard error of the mean. And again, that is a fairly useful way of describing how spread out your data actually are. Bless you. Another way of indicating how spread out your data are is using what is called a box and whisker plot. And we discussed that. Box and whisker plot. It's not whiskers, that's what cats eat. What you have here is you have a set of data, x1, x2, xn, not 8, n. And in order to illustrate your data, what you can do is, in the first place, you can say, I define the entire range. That would be the range of the data. If you order them, that is called a range. You can also then define the median of the data and basically split the data in a lower half and an upper half. You can also then say, right, I take the median of the lower half and the median of the upper half. So we can do something like that. That's this one, median, and that's the median of the upper half. And you can construct a little box. Now, what this box is, from here to here, this part here is called the interquartile range. And again, that tells you the range where 50% of your data are located. And now you can say, right, I want to find out anything that is smaller or bigger than what I would consider an area that is smaller or bigger, where outliers are located. And in order to get these outliers, what you do is you say, okay, I take this part here that I just highlighted, and I calculate what is called the fence. Like a garden fence. This fence is actually this range here, which is 1.5 times the IQR. So anything that is larger than 1.5 times IQR as measured from the upper median, or anything that is smaller than 1.5 times IQR as measured from the lower median, this is your fence range here. And now all you need to do is whether some of your data are lying within this fence range or outside the fence range, I should say. So if you've got a data point here, you would indicate that with an asterisk and you would say, okay, this here is an outlier. Likewise, if you've got a data point here, this would also be an outlier. If you don't have any outliers, what you can do then is you just simply go to your smallest data point, say x1 here, and here you say xn. They are smaller than the fence region, and all you need to do is sort of draw a line to these points here, and you've got your whiskers, right? So you need to find the medians, the median of the whole thing, the median for the lower half, the median for the upper half, bless you. Do your box, and that defines your interquartile range. Calculate 1.5 times the interquartile range and define the fences. These fences help you to identify whether you've got any outliers. If you don't have any outliers, great. You just indicate where your smallest and highest number is and draw your whiskers. If you've got outliers, you want to indicate them as well and say, okay, these are outliers according to the 1.5 times IQR range definition. Okay, happy with that? Yes. You don't have any other options. We also, let me see what else have I got on my list. Yeah. We also defined correlation. So we had correlation, where we looked at dependent and independent data. And we said we usually plot the independent data on the x-axis. This is the stuff that I, as a researcher, can manipulate. And the dependent data, this is basically the result that comes from the independent data. And what we find is some correlation with the data, something like that. We can usually draw a straight line. It would be unusual if you've got lots and lots and lots of data if they are all on exactly the same straight line. And therefore what we can define is how well do the data actually correlate with each other. And to that aim we said, let's look at the data. So in this case, the more of the independent data I have, the higher my dependent value would be. Yeah. So the more of x I have, the more of the dependent data I have, the higher would that be here. And therefore we said this is a positive correlation. What would it be if I say if I have less of the independent and less therefore of the dependent? What would that be? Less dependent, less independent. Sorry? Negative correlation. So I say I have less of my x, and as a consequence I've got less of my dependent. It's still a positive correlation, yeah? So if it is less leads to less, or more leads to more, it's always a positive correlation. And we said the strength of this correlation is usually called R. If it is a perfect correlation, then it would be R would be 1. for perfect. And we would usually consider anything r smaller than 0.8 as not great. Yeah. So anything higher than 0.8 would indicate a strong correlation. What is a negative correlation? Well, negative correlation we would have, again, independent and dependent variable. But in this time, we would say the more of the independent we have, the less of the dependent variable we have. So it would be something like that. So the more of the independent we have on here, the less we would get of the dependent. And that would be a negative correlation. And this would be indicated by r is smaller than 0. Yeah? Happy with that? Yeah, I think we are happy with that. Okay, so that was the correlation. And let's not forget, a correlation does not indicate causation. It just tells us that there is some probably mysterious link between the two data. But exactly what is the cause and what is the effect, we don't know. Remember the example, number of divorces in Wisconsin is strongly positively correlated with the consumption of butter in Japan. Yeah? There's a strong correlation between these two things, but how they are connected, nobody knows. Surely, if you get divorced, people in Japan don't eat more butter, because how would they know that? Yeah? So, be aware, correlation does not mean causation. It could mean, but there's no evidence for that, and that is where research then really starts. Right, what else did we do? Oh yes, the next thing that we did was we looked at a typical distribution of data, and we discovered the normal distribution of data. So we said, for example, we plot how often certain data will appear. So here we have the frequency of data. How often do I get a certain measurement? And here basically is the measurement on the x-axis. And in the case of a normal distribution, I get this normal or Gaussian or bell-shaped curve. We said the middle of this bell-shaped curve, that indicates our population mean. In this case, my drawing qualities are not great. It should be symmetrical, obviously. And a characteristic of this bell shape is that within the 1 sigma range, sigma is our population standard deviation that we've just defined before. Within this 1 sigma range, 1 sigma plus the population mean, 1 sigma minus the population mean. What percentage of our data is in this 1 sigma range? Load? 68. So we've got 68% of our data are located here. How much is located in the 2 sigma range? Loud? 95%. In the 2 sigma range, and in the 3 sigma range, 99.5% in the 3 sigma range. So that's 1 sigma, 2 sigma, and that is 3 sigma. Yeah? So we can say that 68% of our data will be the mean, the population mean, plus minus 1 standard deviation. Or we can say 95% of our data will be the population mean plus minus 2 sigmas. We also defined the z-score. And for that, we said we have our data, x1 minus the population mean divided by the population standard deviation. And that tells us how far away a certain data point is from the population mean of this normal distribution. Now, we then moved on and said we would like to make some inferential statistics. Inferential means we want to do some predictions about data. And we said, okay, we have a population. So that's the population. This population is characterized by the population mean and the population standard deviation. But life is just simply too short to measure every member of this population, so we just simply take a sample, S1, and we take another sample, S2. S1 is identified by the mean of the sample, x bar 1 and x bar 2. And we said, of course, the two samples will be different from each other. So in a way, x bar 1 and x bar 2 will be different from each other because that is the difference between these two. That is the sampling error. And the important thing is that we will never, ever, whatever we do, we will never, ever get rid of the sampling error. It will always be with us. There's nothing we can do about it. But depending on how big the sampling error, how big the difference is between x bar 1 and x bar 2, it could very well be the case that we not have one population, but we have two populations. S1, x bar 1, and that is S2, x bar 2. And in this case, so P1, P2, in this case, we say, okay, we take two samples, and here we have sampling error again. There's nothing that we can do about it. And on top of it, it's two different populations. So the two populations are totally different. So, for example, if you compare humans with aliens, you take samples and you find that the humans are very different from the aliens. Whereas in the first case, you just take samples, you see humans, they are different from each other, but they all belong to the same human species. And we started with hypothesis testing. And in order to formalize that, we said we can start with what we call a null hypothesis. Our null hypothesis. And the null hypothesis basically says the samples, from these samples, we can, in a way, calculate, or we can predict what the population means are. Yeah? So the sample tells us, or gives us a prediction what the population mean is. The null hypothesis says, basically, mu1 is the same as mu2. The population means, as predicted by the samples, are the same. And the only difference that we see comes from the sampling error. Only difference is due to sampling error. Okay, that's our null hypothesis. There is no difference between the population means. Our alternative hypothesis, and I should say null hypothesis H0. The alternative hypothesis H1 can have two different forms. One form is the negation of the null hypothesis. So we can say mu1 is not the same as mu2. That means there is the sampling error and the samples come from different populations. Of course, we have two options for that. This could either mean mu1 is smaller than mu2, or mu2 or mu1 is larger than mu2. Yeah? Because I've got two options, this is usually indicated in the test as a two-tailed test. The other way I can write this alternative hypothesis is H1, I can write mu1 is smaller than mu2. Again, they are not the same. And in this case, I've already sort of prefaced what I've done here. So I said, I'm pretty confident that we are looking at mu1 being smaller than mu2. And if I write the alternative hypothesis in that way, I would only use a one-tailed test. Yeah? So when you are asked what kind of test should I use, a two-tailed or one-tailed test, you would say it depends on how I formulate my alternative hypothesis. From the null hypothesis, you would not be able to tell whether it's a one-tailed or two-tailed test. Only from the way you formulate the alternative hypothesis. Yeah, so please bear that in mind. Yes. In order for describing our data, we also, we said, okay, we have, for example, two data sets. So A1, A2, A3, and so on, and B1, B2, B3, and so on. And we want to find out whether the measurements of these data indicate that they are from the same population or whether they are from different populations. And the appropriate test that you would do in this case would be a student t-test, If the data are totally independent, so if they are independent from each other, A1 is a set of experiments, or A is a set of experiments, B is a set of experiments, and there is no connection between the data, then we would use an unpaired t-test, unpaired t-test. If we have a before and after scenario where I measure basically the same individual before a treatment and after a treatment, then it would be a paired or dependent t-test. Okay? And depending on how I formulate my my alternative hypothesis, it would be a two-tailed or a one-tailed paired test, which uses two different samples, so S1, S2. And because we have two samples, we would call that a two-sample paired or unpaired t-test, one or two-tailed, and for technical reasons, very often people ask also, do they have the same variance, the samples? And you can specify that with or without the same variance. Now, in an exam situation, no. Okay, let's go back. I haven't shown you how you actually calculate manually the whether there is a difference, but what we said is we can use what is called a p-value. The p-value tells us how likely it is that these two samples are the same. And in an exam, I would not expect you to be able to calculate a p-value by hand. I showed you how you can do that in Excel, and that's something that in future years we would expect you to do that, to be able to calculate p-values in Excel. We said in order to make a decision which one of our hypotheses we accept, whether we accept the null hypothesis or whether we use the alternative hypothesis, we compare the p-value with a significance level and the significance level is usually abbreviated as alpha. Very often the significance level, you can also call it as level of, I don't know whether this is an English word, so please correct me, level of unsureness. Is that an English word, unsureness? And uncertainty is a little bit different. This actually, it tells me how sure do I want to be with my prediction. And unsureness in this case is sort of how unsure will I accept to be. Yeah? Very often alpha is set to 5% or 0.05. And we said if p is lower than alpha, if p is low, H naught must go, so H naught rejected. If p is high, if p is larger than alpha, then H naught must stay, exactly. And you have a lovely Australian accent. H naught not rejected. Yeah, so if I give you a p level or p value and an alpha, you should be able to tell me whether you reject the null hypothesis, whether the two samples come from the same population with a degree of certainty or not. Okay? So that was the t value, that was the student t-test. We also discussed what if you don't have data sets, but instead you have frequencies. So you measure certain things and you get different frequencies. So for A, B, C, you get certain frequencies here. And you compare these observed frequencies with expected frequencies. So comparison of observed with expected. And for this you would use a different test. This test actually would be a chi-square test. Square test, and in particular if you have sort of expected from just a theory you would call this a goodness of fit test. Okay? Happy with that? Don't mix student t-test with chi-square goodness of fit test. They measure actually different things. Student t-test looks at looks at two different samples. Chi-square looks at observation versus an expectation. Yeah? Last but not least, we were also talking about a confidence interval for data. And we said if we have a certain data set, we can define our X bar, our mean for a sample, plus minus a margin of error. And you've did that in one of the videos. Margin of error. Very often we will choose what is called a 95% confidence interval. That means if we do the experiment 100 times, 95% of the time, the true population mean will be within this X bar plus minus margin of error. And for the margin of error, this is defined as the t-value, as a corresponding t-value, which comes from the t-test actually, times the standard error of the mean. And you see here we form the loop back to our descriptive statistics. Again, I would not expect you to be able to calculate the margin of error without the t-value. So if I give you a t-value for a certain condition, however, I would expect you to be able to calculate the confidence interval. It's a little hint. You might expect something like that in the exam. Any further questions? No? Are you happy? Wonderful. I can already disclose to you that statistics will come up in the exam and there is no chance to avoid statistics apart from failing. Thank you very much. See you next week.